Ah. And some more full day events like the Seagull Saturday Columbus, Baton Rouge, and Johannesburg, Cape Town, Denver, Minnesota, Orlando, Boston, and so on. Um, I think three of the organizers are from Boston originally, so Boston holds a very special place in our heart. Do come there. It's also one of the best times for you to go and see the colors of the leaves there. So, and Pass Community, November 14th through 17th, is the mothership of all database conferences. I'm sure you'll totally appreciate that. You should come by and check it out. Again, any feedback, please send us an email here, dbavug@outlook.com. If you like to hear a specific topic or a specific speaker, this is a good place to let us know. We are currently all booked up till January next year, but we can definitely accommodate something for February. And without much ado, my good friend Kevin Feasel is going to apply himself as he has done, and he's really awesome. And I will stop presenting, and here you go, Kevin. I will also turn off my video cam now. So,
All right, thank you kindly. Now for me to begin sharing my screens, I have to wait for Teams to refresh and pick the correct screen. So welcome everybody to this session on using the apply operator in SQL Server. My name is Kevin Feasel. I am a Microsoft Data Platform MVP out of Durham, North Carolina. I have a blog called Curated SQL. The idea of Curated SQL is every day I try to find and link to 5 to 10 interesting posts on topics all across the data platform space. So it's curatedsql.com. I also have a one-man consulting shop that allows me to do stuff like this because I am my own boss and I can't tell me what to do. So the apply operator. By the way, if you have any questions or comments or anything throughout, drop them in chat. I have chat right in front of me. I'm looking at it right now. Over here are my slides. Right here is chat. But the basic idea of the apply operator is this thing is semantically similar to, but not quite the same thing as a join. So there are two flavors of apply that were introduced in SQL Server 2005, cross apply, outer apply. Cross apply, semantically similar to an inner join. Outer apply is semantically similar to a left outer join. There is no equivalent to like a right outer join or a full outer join with apply. And as I explain what the apply operator does, you'll understand quickly why that is the case. So the next thing I want to talk about is why are we here? Why are we even talking about the apply operator? And because it's a good thing to talk about. Here's a quote from Adam Mechanic. I had a chance to talk to Adam a while back. It's been several years now, but I mentioned that, hey, I used one of your quotations in my talk. And he's like, yeah, I still agree with it. So I got that seal of approval. The idea is if you do not understand the apply operator, then there's a lot that you can pick up. There's a lot that you can learn from it. There are specific scenarios in which it is the best choice, other scenarios in which it's not a great choice, but it does solve a number of problems in a rather elegant manner. And we're going to talk about several of those problems today. So the first thing I'm going to do is joining to functions. And this is what I would call the 2005 version of apply in terms of how we thought about the concept. So the apply operator, when it first came out, we had some early books, the stuff that was written in 2006, 2007, that basically said, oh, well, yeah, you can use apply to connect to a table valued function and treat it like a table. And then that maybe was 3 lines in a book of 400 pages. And that was all you needed to know about apply. So this was the initial example. And so let me give you an example here. We have some dynamic management views and dynamic management functions. One DMV is sys.dmExecConnections. I can select from that dynamic management view and get information on what are currently running sessions. But I can't get query text. I can't get execution plans. Those are hidden behind dynamic management functions. And in order to connect this dynamic management view to a dynamic management function, I need to use a join or an apply operator. So let me show you what we can do. If I try to use an inner join, and inner join like dmexec SQL text, and I try to pass in the most recent SQL handle, what's going to happen is I'll get an error, a syntax error that says you can't pass in parameters to a dynamic management function when you are using an inner join. Now, if I don't have any parameters, I could technically run this. If I could use all defaults, or if I don't have any parameters for the function, inner join could work. But because I require a parameter, inner join is not going to work here. Our solution instead is to use cross apply. So we have dmexec connections, and we cross apply dmexec SQL text, and I take that C, the alias for DM connections, and pass in the most recent SQL handle into the function, and it executes for each record in dmexec connections, and it gives me back a result that is T. So we have our cross apply operation, and I can reference the table C, obviously, in my select clause, just like a regular table or DMV. And my output of the apply operation is another table that I can use. So from SQL exec SQL text, I can get the actual text of the query that's being run. And let's take a quick look at that in demo form. So here I have, by the way, if you need font size bumped up, just let me know in chat. And here I have dmexec connections. So dmexec connections, I've got quite a few of these running here. Not a whole lot of interesting stuff going on. This is just a local box, but we can see that I have plenty of sessions. Now I can say dmexec connections and cross apply. So I talked a little bit about cross apply and inner join and semantic similarities. Now I want to talk about what exactly is going on with the apply operation. What's actually the purpose here? And so the idea is that from a left-hand side table, we are going to take each row of that table and we are going to execute a function against each record in that table. And I'm using table in a very generic term here, where it could be a table, it could be a view, it could be the output of a common table expression, it could be a virtual table generated from a set of values, whatever. But the idea is that we're going to execute a function. So this function f, and I'm going to scribble one f here, and f runs for each one of these. F in this case is dmexec SQL text. So for each row in dmexec connections, like that session right there, we're going to execute this function, passing in the parameter most recent SQL handle, which is right over here. And with that, we'll be able to get back some results of text that's being run. And you'll see that I get 17 rows back. Now, if I just query dmexec connections, I have 105 rows here. So what's going on? Well, what's happening is that cross apply is semantically similar to an inner join. If I don't have a most recent SQL handle, then I'm going to get an error, or not an error, excuse me. I'm going to get a row that doesn't have any value returned back. It's going to be null, and therefore we'll get no row in the corresponding output. And when I try to connect these two together, that row disappears. So we drop down to 17. But what if I change this cross apply to an outer apply? And what I can do, let's say I'm going to pick session 53 because we can see session ID 53 exists. So if I do cross apply on here, session 53 does not exist.
Kev, give me 1 sec, okay? Sorry.
Sure.
Hey, Mike Bird, can you turn off your video, please? Thank you.
So with cross apply, we dropped that session 53, but outer apply will include that. So we can see that session does exist even though the text output is not there. So that's a real quick idea of what the apply operator is doing. And lessons learned. Number one, we can use apply to execute a table valued function as if it were a table. And number two, we have outer apply, we have cross apply. We have those two flavors. Now, if this was all that you could do with the apply operator, join to table valued functions, it would have some meaning. It would have some value, but it wouldn't be worth talking about because let's be blunt. Dynamic management functions and joins to those are useful. That's good. Creating our own table valued functions, usually not a good use of time, definitely not a good use of resources. Almost always performance is going to be considerably worse than inlining a query. And so I couldn't in full conscience recommend that, even with some of the changes that have happened in recent versions of SQL Server around Freud, around trying to make inline table valued functions more performant or scalar functions more performant. Still not good enough. But thankfully, I don't have to focus on table valued functions. This is actually the last time I think I'm going to use a table valued function in this talk because I don't like them very much. Instead, we're going to see how we can create virtual functions and use the apply operator to help us out there. So let's talk practical use case, pre-aggregation of data. So I have some data. I have, for example, water bottles that are sold as part of this AdventureWorks data set. And I want to figure out how many times has somebody ordered a water bottle from the AdventureWorks store. And I want to also figure out what product category, what product subcategory do these things belong to. And I can go study the schema. I can go write some queries, go into my thinking corner, come out with an execution plan based off of a query, kind of like this. So we have a table, product category, and we interjoined a product subcategory. We interjoined a product. We interjoined a sales order detail. Assume that the keys are correct. I'm not trying to trick you here. And then I'm going to filter where the product is a water bottle, 30-ounce water bottle. I'm going to have my select clause. That select clause will have the category and subcategory name, the product ID, the product name, and also a count indicating how many times did we purchase this water bottle. Well, I have an aggregated column using an aggregation function count. I have non-aggregated columns, and therefore I need a group by clause, which includes all of those non-aggregated columns. And then finally, I'll order it by name so that I have clarity in the world. So that query right here, this runs. It executes. It gives you the correct results. There is no inherent problem with this query. But I'm going to show you another query. This one uses the apply operator. So we start out pretty similarly. Category joined a subcategory, joined a product. But now I'm going to introduce a cross apply. And this is a virtual function. What I mean by a virtual function, what the literature means by virtual function, is this is actually considered a function, but it only exists within the context of my query. So within my cross apply, I have a select statement. That select statement says from sales order detail where the product ID on SAD, sales order detail. I don't know why I typoed and had SAD instead of SOD, but whatever. But where the product ID matches. Well, product comes from that table up here, production.product. So we can join in, we can bring in columns that exist outside of our cross apply expression and introduce them in here. So I can see it's part of the where clause, and I can get my count. I can bring up here, have the category name, subcategory name, product ID, product name, and detail count. So notice that the aggregation is down here in the cross apply. Up here, I have a select clause, but I don't have an aggregation function. So I don't have a group by clause at the end. And let's see what that does to our queries. So pre-aggregated data. I am not going to turn on execution plans. What I'm going to do is bring these into Century 1 Plan Explorer, and I need to get the correct database. That should be the correct database. And so we run these queries, and I have two queries that run. And by the way, in case you have any questions about the results are exactly the same. That's going to be pretty well a guarantee. So let's look at execution plans. This is the first execution plan. And in here, we have product. So this is just getting our product details. We have joins to product category, product subcategory. And then we have here one row, which is our water bottle. And we need to go grab the records from sales order detail. This is an enlarged version of the sales order detail table so that I have more rows to play with. That's why I get back 187,520 rows. Well, this is a nested loop join. Basically, it's a for each statement. So for each record in here, go and grab all of the relevant records in the underlying table. That gives us a total of 187,520. Then we get the count, grouping them all together. We return those values and we can complete our select operation. So that's what this plan looks like. By contrast, the plan for the apply operator looks a little different. Up here, this is exactly the same. It was just interjoining some tables together. So that didn't change at all. What changed is this nested loop join, because we now have our data that is pre-aggregated. The aggregation happens before this nested loop join, before this apply operation occurs. And as a result, we now have, instead of one row joining to 187,000 rows, we have the aggregation happen here and we join one row to one row. And this is why it took about a quarter of the time to complete. So CPU was significantly lower, but IO is exactly the same. We still have to read the same number of rows. We still have to do the same amount of processing work. But by aggregating earlier on, we make this later join, which is a relatively more expensive operation than just aggregating. We make that less expensive and pass the savings on to the consumer. So pre-aggregation here allows us to get a faster result for a query because we're able to end up joining together smaller subsets of data. Things that we picked up. Number one, we can use apply not just on the fully defined functions that you create as like create function, blah, 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 as table, blah, blah, blah. But we can also get them from ad hoc or derived or virtual functions. I should also note, this is not the only way that you can pre-aggregate. You can also use things like correlated subqueries. So you could have a subquery that's going to retrieve this data, that's going to perform your aggregation. The subquery will perform exactly the same, assuming you write the subquery correctly. So there's going to be no performance difference in this case between the correlated subquery and this apply operation. In this case, I have to stipulate in this case. We'll talk a little bit more about which cases this makes sense in, but I want to make it clear. This is not broad-based, go change everything to apply operations. But in this case, apply worked better because we were able to aggregate early and reduce the stress on that nested loop join. Reduce the number of rows that we're going through that join. And by the way, if there are any questions, you're welcome to drop them in chat at any point in time. But now I want to talk about getting a child record. So here's our problem. We want to see for each customer, that customer's latest order, the PO number that's associated with that order, and the total amount due on that order. So if I have 1,000 customers, I want to get up to 1,000 rows back. There are a few options that we have, and we can go to the thinking corner. We can kind of try out different things, but I'm going to cut to the chase here. 3 options that are set based, 2 options that are rebar, row by agonizing row. The 3 options that are set based, I can use a nested subquery. I can use a common table expression with a window function. I can use a derived function using apply. Now, my rebar examples, I could use a while loop or a cursor. I could also have a more complex situation where I create a set of subqueries and save the results into temp tables and then combine the temp tables together. So I've got quite a few ways to solve this problem. But I want to avoid the complex solutions like create temp tables and load a bunch of data into them. I want to avoid rebar unless I absolutely need it. And so we're going to focus on the 3 set-based solutions. And then we'll see if any of those is practical for the job. So let's jump to the demo. Okay, so here's my query. I want to figure out for each customer their latest order, PO number, and total due. Well, here are my customers. How many customers are we dealing with? We have 19,119 customers. And so that's customer joined a person. So I also mentioned that I have a few different options available. And to make the best case for each of them, I'm going to create a helpful index on sales order header based on customer ID and sales order ID and include the columns that we need. So this is appropriately indexed. We're not going to have a missing index that changes the story drastically. Let's double check that. We'll make sure that that index exists. Okay, index already exists. So we're good. Method number one, correlated subquery. Sales.customer joined a person, and we have a left outer join. Inside this left outer join, I have some parentheses, and inside here, I say from sales order header, give me the customer ID and the max sales order ID. So I'm taking advantage of the fact that the latest order for a customer happens to have the maximum sales order ID. And the relationship here is that there's a monotonically increasing relationship between the date and the sales order ID. So in other words, if I have 3 orders along this line, then I know that the order ID will, for this last order, will always be bigger than this one, will always be bigger than that one. And that will hold true no matter what. So I'm taking advantage of that relationship. If that relationship didn't exist in this scenario, this query is a lot harder. But I've got this aggregation, and I'm going to join on customer ID. So this customer's ID is equal to my SOH max's customer ID. And technically, this is not a correlated subquery. This is a lie. This is a nested subquery. So, or a non-correlated subquery. Because for it to be a correlated subquery, I need to reference something from up here within the subquery itself. A quick trick, if you can run the subquery and not get a syntax error, it's not correlated. Okay, left outer join sales order header. Why do I need the second one? I need the second one because I need the PO number, I need the order date, I need the total due. And for this, I have a customer ID, I have a max sales order ID, but I don't have those details on the sales order itself. So I need to join back to sales order header and get those details. So that's method number one. I want to run this and show you it does give me back 19,119 results. It gives me back these orders. So we do have valid orders. Next option, window function. So I can take from sales order header, I can say, give me your customer ID, your PO number, your order date, and give me a unique monotonically increasing value for each customer. So based on each customer, sorted by their sales order descending. So in other words, the person's last sales order was 1. Their second to last sales order was 2, and on and on. So Lars, the quick trick's saying that it's not correlated. If I can take this subquery and just run it as is and not get a syntax error, then it is not a correlated subquery. It's a non-correlated subquery. By contrast, let me show you this apply operation. Because I have an outside column in here, if I just try to run it, I'll get an error. So that's the idea. So, all right, my window function. I run this, and we have for each customer a row number that represents the latest order being the lowest. So for customer 11,000, that's their latest order. For customer 11,001, we reset. Here's their latest order. For 11,002, here's their latest order, and so on. So then we can take each one of these and we can say, give me customer joined a person, left outer joined to orders. We don't know if the person's made an order, so we want to make sure that we get those results back, even if they don't have an order, on customer ID and row num equals 1. So only give me back the records where row num equals 1. And I run this, and it comes back, and I'll tell you the results are the same. Finally, apply operator. So here I have customer joined to person, and I have an outer apply. Outer apply says from sales order header where the customer ID matches. So where this customer ID matches sales order header's customer ID, give me the top one set of values ordered by sales order ID descending. So here's my virtual function or my ad hoc function, and I can execute that for each customer. So I run this and I get results. And again, the sorting may be different, but the results are the same. And I'm going to take these, I'll put those into Plan Explorer. And as I put them into Plan Explorer, we can all talk about how, obviously, considering that this is a talk about the apply operator, the apply operator version is certainly going to be the best. It's absolutely going to perform the best in every scenario. And okay, let me run this here in Azure Data Studio. What's going on is Plan Explorer is going to take each one of these function calls. There's actually a computed column that's a function, and it's going to take forever trying to analyze that function. So instead, let me just bring this into Azure Data Studio. And we have three queries. Number one, this is our correlated subquery. Number two, this is our window function. Number three, this is our apply operator. And you say, hey, query cost relative to the script. This is a talk about the apply operator. Why are you showing me a query where apply doesn't do well? And actually, once this finishes up, okay, cool, it's finished up. We're going to see a little bit more clearly what the results look like. And again, first query, correlated, not non-correlated subquery. Second one, common table expression. Third one, apply operator. So CPU-wise, they're all about the same. They're close. But we can see with reads, that doesn't look good. We have 2 orders of magnitude more reads with the apply operator. And now I want to help you understand why that is the case. So let's look at execution plans and try to understand that why. Step 1, subquery. So we have customer joined a person. This box, ignore that box. That box is going to show up for each one of the queries. It is the same for every one of those plans. So I can just ignore anything that's in there. So what do we have? We have a scan on sales order header, a stream aggregate. That's how we get the max value. But then I need to join it back to sales order header to get the rest of the values. And then I'm going to join those together, get my 19,119 rows, connect those with the customers, and return back our results. So we're scanning that header table twice. With our window function, we scan sales order header once, and then do a little bit of segment, sequence, project, compute, scalar. Usually if you see these three, you're doing a window, you've got a window function in there somewhere. And we're filtering from 31,000 rows down to 19,000 rows. So in other words, there were 31,000 header rows in this table altogether. We got rid of about 12,000 of them, retaining roughly 19,000. And then we join and we send back our results. For our apply operator, what are we doing? We have the same block as the other 2 queries, and then we do a nested loop join, because what we're saying is for each row in customer joined a person, we are going to perform an operation. We're going to go look up, give me the latest order for that person. So we're doing this 19,000 times. Each individual lookup is, 3 reads maybe? But if I do 19,000 reads, 19,000 times 3 reads, I get a whole bunch of reads. Even if it's just 2.5. That's how we get to 42,000 reads versus 400 reads. So scanning that table once makes a whole lot more sense than seeking it 19,000 times. And now let's take a step back and try to come up with a better answer. So I actually thought I had a slide in there, but apparently I don't. So instead, let me give you a second scenario. We still have 19,119 customers. But instead of looking at that sales order header table, let's look at this enlarged table. The enlarged table has a lot more rows. And what I'm going to get at is as the percentage of records that you want to return changes, then the emphasis on whether you should seek versus scan shifts. So let me give you a little number line here. So this is a number line. This represents percentage of rows that we want to retrieve. Down here at the end, this is 0. Down here at the other end, this is 100% of rows. Now, there are 3 sections, 3 regions that I want to mention. Region number 1 is just scan the table. Region number 2 is just seek the table. Region number 3 is, I don't know, you could do either. It's going to depend. So the question is, where do these regions meet? And rule of thumb, the scan, this is about 20%. At this point, roughly 20%, just scan. The seek zone is like right there, 0.5%. And the in between is could be either. Could be scan better, could be seek is better. So if we're only retrieving like 0.5% of the data, we almost certainly want to seek. If we're retrieving 20% or more of the data, we almost certainly want to scan. If we're retrieving 1/2 to 20% of the data, maybe we seek, maybe we scan. We're going to have to test both and see which is better. Remember that we were retrieving 80% of the data here. So we were getting the vast majority of data, which is why a scan was so much more efficient. Well, let's try a different approach where we still have our 19,000 customers, but instead of having 31,000 rows, we're going to have a lot more. If I remember right, it's roughly 1.25 million rows. And if you do the math, you're going to end up with something that's much closer to 0.5% of the rows that we want to retrieve. So let's quickly run these in Plan Explorer and also run them in Azure Data Studio. Results, we still have 19,119 rows for each of the 3. My execution plan, now we can see that the estimated plan doesn't like the correlated subquery version or the non-correlated subquery version anymore. It doesn't like the common table expression, but it sure does like the apply operator. And once Plan Explorer comes up, we'll get the exact numbers. But while that's happening, let's talk about what's going on here. Step 1, this is the same as before. Customer joined a person. Nothing has changed here. Still have 19,119 rows. But notice that the shape of this plan is different compared to before. Before, we had sales order header, joined to sales order header, and then eventually joined to customer in person. Now, because we're going for 1.25 million rows, we actually want to get the person first, and then we do a nested loop join against sales order header to get the max row, the max sales order ID for that person. So we do 19,119 nested loops, and then we do a hash match, which scans the entire table, brings back all 1.25 million, and winnows that down to 19,119. So we're essentially doing 19,000 seeks of the table plus 1 big scan of a table. Let's look at the common table expression version. We still have just 1 scan of 1.25 million rows, segment, sequence, project, and compute. And then after doing all of this compute work on 1.25 million, we get down to the 19,000 rows that we need, because we don't know which value will have row number equals 1 until we perform this operation. So we can't understand beforehand which row will have row number equals 1. We have to scan through the whole table to figure that out. So we do that scan, we get 19,119, and then we have our customer data, and we join it all together. So there we go. We saw those two plans. So we saw this plan, big index scan. We see this plan, big index scan. This plan is the apply operator plan. It looks exactly the same as before. The apply operator didn't change its shape. And as a result, when we look at CPU time, the apply operator version is taking half the time of the other two. Now, as far as reads go, yeah, this one is still fewer reads. But if you're CPU loaded and you're running on fast disk, which is usually the case, that apply operator is going to perform better. And here's the real trick. That was at 1 million rows. Now imagine if it's 12 million, 100 million, 2.5 billion. At that point, every order of magnitude you increase, apply gets that much more efficient, and your window expression gets that much less efficient. So window functions don't scale extremely well. As you need to scan an entire table, as that table gets bigger and bigger, that can be a performance impediment. The apply operator has a fixed scale, as a fixed size. If you index things appropriately, if you have an index seek operation on here, and basically saying we're performing based on how many rows do we have on this outside, this outer loop of the nested loop join, and how many records, what percentage of the records do we need to get from the inside part. So the moral of the story here is, as you have fewer rows in the outer loop and you have a lower percentage of records you want to retrieve from the inner loop, the apply operator does better and better relative to its peers. That's my lesson learned here. Nested subquery ends up being inferior to common table expression with a window function. Basically, having a window function beats not having a window function in both of those versions. I do say the common table expression is easy to understand. That window function, easy to understand, easy to explain. I like the apply operation, how it looks as well. So aesthetically, I like both of them. But the apply operation tends to scale better. If you know that you're going to have massive growth or you already have a large table, the apply operator is probably going to work better for this type of query than a window function. So with a small data set, pick whichever one you like nicest. With a large data set, you're probably going to want to try out apply. Now, this becomes even more true as we expand beyond the simple case of give me the latest row, and instead say, well, what if I want not just the latest row, but the 5 latest rows? So now I want to get the average, the min, the max. I want to get total prices of their 5 latest orders per customer. And again, I can try to solve this problem the same way. I don't have new approaches to just come up because I need 5 instead of 1. But actually, what I'm going to say is that approach is not good. Not for multiples, because I took advantage of a mathematical relationship to even get this nested subquery to work effectively. So we're going to focus on these two. And again, the window function is important, not common table expression. If I had a nested subquery with a window function, it would perform the same. So window function, derive function with apply. We're going to try those out. And I'm not even going to waste a lot of time on this variant. I'll say for small tables, this is going to perform, the common table expression is going to perform better. And here's what's changing for this query. I have my common table expression. I still have row number. I have customer ID and total due. Then down here, I have customer joined to person, and I'm left out or joining on orders where row num is less than or equal to 5. So that 1 changed to 5. So I'll get up to the 5 latest orders. If you only have 4 orders, I'll get 4 of them. If you have 2, I'll get 2. If you have none, I don't get anything. If you have 12, I get the latest 5. And we're going to perform some aggregation. We have some non-aggregated columns, so we need that group by clause with our non-aggregated columns. And I'm going to run this. We'll get back our results. 19,119 of them, just as we expect. The apply operator variant, here's how it looks. Sales customer joined a person. We outer apply, select the top 5. I don't like what past me did there. Top 5, customer ID and total due from sales order header, where the IDs match, the customer IDs match, order by sales order ID descending. So the only change that I made here, instead of a top 1, is a top 5. So in both of those cases, the going from the specific case of give me the latest to give me the 5 latest, the more general case, was nothing more than a change in a number. Easy for both of them. I still have my aggregations. Note that I'm doing my aggregations outside of the apply operator and my non-aggregated columns. I have group bys. And I will say, we're getting practically all 30 some thousand rows. It's like 29,000 out of 31,000. So out of all of these, we're getting almost 95% of the data, which means this variant is going to be much faster. I'm not even going to run through the performance analysis. I'm not going to try to wow you guys. Just note that with smaller data sets where you're getting a larger percentage of the lower tables total, you're going to want to scan rather than seek. But as we increase the size of the data set to get our 19,000 results, we have, remember, 1.258 million rows. And as I do that, let's bring this version into Plan Explorer. And this is going to be a little bit more interesting, because what we're going to come back with is roughly 90 some thousand rows. So these are still running. It's still putting together the execution plans, which is why we don't have durations yet. But we're expecting to get back 95,000 rows. And my mouse is hovering right over it. We're going to get back roughly that number. So 95,000 out of 1.25 million, if you do that math, it is roughly 8% of the data. At 8% of the data, we're in that it depends zone. So remember, 0.5%, definitely seek. 20%, definitely scan. Rules of thumb. And then in between, could be one, could be the other. And I'll let that run. It's going to have to tally all the results of the function calls. But basically, what we'll find out is that between the two, if I remember right, there may be a minor difference between the two, but it's pretty similar. And that kind of plays into that rule of thumb that we're talking about. So for this general case, our real change is, instead of top 1, it's top 5. Otherwise, queries can be the same. It's what we do with the data afterwards. Now, because I have a moment as it's loading all of this, I will note, why are we performing this aggregation outside of the apply operator? And the reason is, I need to be able to get those 5 rows before I can aggregate them. So I need to discover what those 5 rows are, then I can aggregate them, and then join them. And I could do a couple of things to maybe reduce the number of rows and possibly eke out a little better performance here by pre-aggregating, but I'm not going to get an enormous advantage, because we're not going from like 187,000 rows down to 1. We're going 95,000 rows down to 20,000 rows. So minor advantage, but not a huge CPU difference. So, all right, here's what we've got. If I zoom in, we can see that the apply operator version has a lower CPU utilization, but it definitely has more reads. And again, that makes sense because we're doing 19,119 index seeks versus 1 index scan. In this case, Yeah, I have one big index scan here. So fewer reads. If you're really IO heavy, you're running on slow disks, this variant may be better for you. If you're running on fast disk, you've got flash arrays or really good solid state, but you're maybe more CPU dependent, this variant could be better for you. And you can see that the two perform roughly the same in terms of wall clock time. Um, what that's telling us is that all in all, either one could work, and we're at that knife edge of which is going to perform better. And the answer is at this data size with this query, they're pretty similar. You can make an argument for either one. As the number of rows increases, however, this apply operator will get relatively more efficient compared to the window function. So for that reason, if you expect that this table is going to get much larger, go with the apply operator. So when is apply more efficient? Here's the slides that I was thinking about. So it's not always more efficient because apply is running for each row on the left-hand side. And each iteration is unique, so you can't take all the rows at once and then join them together. You have to actually perform the loops. Those loops are not the same as a while loop in T-SQL or a cursor in T-SQL. Performance is considerably faster. There's a lot more going on with a T-SQL cursor loop than just a loop. So don't think of them as the same thing. The apply function performance tends to be significantly better than a cursor for most tasks. Our ideal apply operation: relatively few parent rows, relatively many child rows, and relatively few interesting child rows. So that's my simplification of what we were talking about before, where if you think of that nested loop join, the parent table should have relatively few rows that we care about. That can be after a where clause, so we can filter to get just the ones we care about. Then we want a very large child table of which we care about a very small percentage of the data. If you have those conditions, apply is probably going to be your best option. So a scenario like this, where I'm getting 19,000 rows, but we've got a table of 100 million. For our aggregation, our pre-aggregation, remember that we had that nested loop join of 1 to 1. So by pre-aggregating, we got it down to a 1. If we had to nested loop join and get all 187,000, we saw what the performance looked like. And here's the image that I was thinking about that I drew back together. But our seek zone, less than 0.5%, our scan zone, 20% or more, it depends in between. Again, these are rules of thumb. It may not be exactly 0.5%. It may be something that's a little bit different, but consider that as a starting point. So consequently, apply is going to perform poorly if you need a table scan for each parent row. So if I needed to scan sales order header enlarged 19,000 times, that's going to be terrible. So I need appropriate indexes so that when I do my lookup, it's a seek instead of a scan. If I have a huge number of parent rows, probably not going to perform well because we're scaling number of parent rows times number of pages read to pull in data for one parent row. Or if I need to retrieve practically the entire table, I'm essentially doing in scan or seeks of the table, range seeks of the table instead of one scan. And one scan is going to be more efficient instead of 20,000 seeks that take up basically the entire table. Last thing I want to talk about here, I've got about 9 minutes. I want to simplify some calculations. SQL Server calculations tend to be rather repetitious. We tend to have the same calculations pasted in many places and many times. And apply can help us by doing a couple of neat tricks. So I have here a sales order detail table, and I have a list price, order quantity times unit price. And then I have order quantity times unit price used in multiple variants. And that kind of sucks. I also have this order quantity times unit price times the quantity 1 minus unit price discount to get the calculated line total. And then I use it again here, and I use it again here. So I'd like to be able to not have quite as many repetitive calculations, especially because copy paste could get it wrong or the calculations can change in the future. Here's what I can do. From sales order detail, I can cross apply, and without a from, I can say select order quantity times unit price and call that list price. Without a from clause here means that my function doesn't go look up more data. There are no additional seeks, there's no additional IO. And really, there's no additional compute because this is all wrapped into a compute scalar, which I need for the calculation to begin with. So then I could take that list price and I can use it in my main query, lp.listPrice, lp.listPrice times sod.unit price discount. Well, I can also use it in another cross apply operation. So I can chain cross apply operations and use the results from a prior apply operation in the next one. So I can create a calculated line total. And then I could say, well, take calculated line total, of course, use it in the select clause, but also in the next cross apply, calculated line total minus the line total as calculated difference. And I could show all of this stuff in my query itself. So I can show all of these in a easier to read manner. I think this variant is easier for us to read and understand what it is that we're trying to get. Oh, here's the discount amount. Here's the calculated line total, the difference. Does it have a difference that's meaningful? It's more than 1 cent. And if I need the specific calculations, I can go into the cross apply functions and read them. But up here, if discount amount, calculated line total, calculated difference, if these are just normal terms, business terms, then a business person who's reviewing a query or a slightly technical user who knows more about the business side than maybe writing great SQL code can at least look at those terms and say, oh, yeah, no, that's exactly right. Yeah. Of course, calculated line is the list price times 1 minus the unit price discount. So let me show you another example. For this one, I'm not going to show Plan Explorer anymore. We're no longer concerned so much with performance, but instead, how can we make our lives better? So I have a fact table. And by the way, this is real. Was real at one point. I ripped it out eventually. But we have digital marketing data. And we have two sources of information for clicks and cost. So every time somebody clicks on an ad and how much money the advertiser is paying to get somebody to click that ad. So how much they would pay Google to display that ad enough times for someone to click on it. Now, there were two sources of information, and we would get information in from these two different sources and try to combine it together. Meanwhile, on our side, we knew how many orders there were, what the revenue was, and what the product cost was. So given these two click sources and cost sources, we had a Boolean flag that would say, do we want to use the first source or the second source? Because the data itself didn't necessarily tell you which source it was. Sometimes we had one, sometimes we had both, sometimes we had neither. But at least that flag would tell us, no, use source 1 for this one, use source 2 for that one, use source 1, use source 1, use source 2, etc. And this was a simplification of the real table. And from fact, I have these calculations, and I'm not even gonna tell you what the calculations are doing, except take 3 seconds and tell me what happens with conversion rate. And I'm gonna say probably nobody in here knows what conversion rate is doing here, and that's fine. It took me a while to figure it out. I had to go dig through, and let me talk about what the problems are. Problem number 1, there are all these is-nulls. Is-null everywhere, and it's annoying. Incidentally, the is-nulls were actually required even though we had sums, and it was just the dumbest reason. It was that the data access layer that was written in C++ a long time ago, when it would read SQL Server result sets, it would take the result set from here, and it would look for any warnings or error messages. And there's a warning if you don't have is-null that that nulls are removed from aggregates, that they're not included. that warning message would get interpreted as a second result set, and the data access layer would throw a hard exception saying, you gave me 2 result sets, I only expected 1. So instead of fixing the data access layer, they slapped is null in every place because that was a lot easier to do. So we have is null. Second, we have these calculations like case when use source 1, then whatever else, whatever. That shows up multiple times. That exact calculation shows up multiple times. And then here is for cost. We can see it here. We can see it there, there, there. So I want to be able to try to simplify this a bit. But I will say, we do get back results. So it is a valid query. And apply is going to help us clean this up. So let's come down here to fact. And we say cross apply. First thing I want to do, I want to take all of those is null operations and just put them in an apply block. So I select is null, click source 1, click source 2, et cetera, just call that no null. I no longer care about null. Everything is protected from null. Then I can use another apply block and say, when use source 1, then give me click source 1. Otherwise, give me click source 2 and call that thing clicks. If I use cost source 1, or if I use source 1, then give me the cost for source 1. Otherwise, give me the cost for source 2. Call that thing cost. And then that's US1 for use source 1. So with these 2 simplifications out of the way, here is what my results look like now. Sum of clicks, orders, et cetera. Here is conversion rate. Conversion rate is now saying, hey, if you don't have clicks, your conversion rate 0. If you don't have orders, your conversion rate 0. If you have somehow more orders than clicks, conversion rate's 100%. Otherwise, it is the number of orders divided by the number of clicks. That's the conversion rate. Now it's a lot simpler for a human to understand and say, yeah, that's correct. Because sometimes we flip things around. We say like clicks divided by order count on accident, because in this query, are you really going to be able to tell me for sure that I did it wrong in a code review? Probably not. So the 2 queries, just in case you are curious, execution plan for one. The execution plan for the other includes a loop join and a constant scan, which is a little weird, but otherwise it's the same. Performance-wise, it's the same. They both are going to perform just the same. So I don't care about performance here. But as we can see, by doing this, we seriously simplify a real-life query into something that is much more understandable for a human. And if we need to understand where no null comes from, I can say, oh, it's down here in the supply operation. I can go look at it. But otherwise, I can focus on the select clause and make sure that my calculations are actually right. So we can use apply to remove repetition from calculations. And as we're getting to the top of the hour, let's wrap things up. So apply is going to excel at a few activities. Data pre-aggregation, subsets of child records where you need to get a set of child records for each parent record, or simplify calculations without losing performance. There's another example I did not include of splitting strings. And this is not a cure-all. This is not going to be change all inner joins to cross-apply, change all left outer joins to outer apply. Don't do that. That's probably not a good idea. But be sure, when you're writing code, if you run into performance problems, try out a few different ways and see what performs the best, because it could be apply. It might be something else, but it could be apply. If you want to learn more, you can grab the slides, the demos. You can grab resources, links to additional resources at csmore.info/on/apply. If you have any questions afterwards, please do feel free to email me, or you can hit me up on Twitter should you like. This particular course, I'm going to take it off and eventually make it available for free. And if you have questions, you want to pay me money to yell at servers, that's how you can do that. But with this, I'm here for questions. I know Paresh has to drop off, but I want to say thank you all so much. And if you have questions, drop them in chat. I can stick around however long you've got questions.
So I'm going to stop the recording now. I can only figure out how to do it. Yes. Stop recording. Julie can possibly hang around a little.